10.3 Arcs and chords. Points on a circle determine both arcs and chords. Several properties are related to points on a circle. In a circle or in congruent circles, two chords are congruent if and only if their corresponding chords are congruent. Two arcs are congruent only if and only if their corresponding chords are congruent. And the if and only if means it goes both ways. That if two arcs are congruent, then that means their corresponding chords are congruent. So in this image here, or this diagram, we could see that we have arc RT and we have arc SV. RS is what we're looking at, and we're also looking at TV. And so if TV is congruent to RS, then that means that the length of RS is equal to the length of TV. And also the flip side is if the two chords are congruent, then that means that the arcs are also congruent. So let's go ahead and look at this example here, circle K. And we're given that arc AB is congruent to arc CD. We could see the lines that we're accustomed to marking their congruence. And now we need to find AB. Okay, so now we need to find not arc AB, but the chord AB. So since we know that the arcs are congruent, then that means that the chords are congruent. So we could say CD is congruent to AB, which means that the length of CD is equal to the length of AB, which means we can create our equation. Because we have an expression for the length of CD, we have an expression for the length of AB, and our equation, if we substitute in, is going to be 2x plus 3 is equal to 8x. Now we could solve for x, and we could find the length of AB by substituting in for x there. So I'm going to subtract 2x from both sides. I get 3 is equal to 6x. And then dividing by 6, I get x is equal to 1/2. So if x is equal to 1/2, then what is AB equal to? It's equal to 8 times 1/2, which is going to be 4. So we have AB is equal to 8x, which is equal to 8 times 1/2, which is equal to 4. And we're done. So we can use the properties of congruent arcs and how they relate to congruent chords to solve problems. And so here's our next set. Diameters and chords. So in a circle, if a diameter or radius is perpendicular to a chord, and remember perpendicular means forms a 90-degree angle with the chord, then it bisects the chord, and this means cut in half, right, to bisect. And it also cuts the arc in half. So if we look at this diagram here, we could see that the diameter, WZ, is perpendicular to chord AB. And what does that mean? That means that AX is congruent to XB, and that also means that arc AW is congruent to arc WB. And the same thing is happening down here at the bottom. Okay, in a circle, the perpendicular bisector of a chord is the diameter. So it goes the other way around. Right? If we have a chord RS and we know that we have a perpendicular bisector here because it's perpendicular, and if it bisects, that means that RY is congruent to YS. If both of those are true, then we know that ZW is the diameter of the circle. So it goes both ways. Right? And then in a circle or in congruent circles, two chords are congruent only if they are blank from the center. Equidistance, I would say. Equidistance. from the center. So AB is congruent to RS if and only if XO is congruent to OY. Right? Now, and also it's if and only if, so it works the other way. If we know that AB is congruent to RS, then we can say that XO is congruent to OY, and also if OY is congruent to XO, then we know that the two chords that are formed at that distance away are congruent. Okay, so let's go ahead and use those properties to solve some problems. And so here we have this circle O. We know that CD is perpendicular to OE. Okay, great. That gives us a lot of information. And then we have OD is 15 and CD is 24. Okay, so what are we supposed to find? A diameter or radius perpendicular to a chord bisects a chord. Yes. So OE bisects CD because it's perpendicular to the chord. So ED is congruent to CE. And so we're trying to find OE. Right? And in order to do that, we first need to find ED. Okay. So then the length of ED is going to equal to 12 because CD is 24. Then because OE is a perpendicular bisect, it is perpendicular to the chord, and its endpoint is in the center of the circle, we know that it bisects CD. Right? So then ED is equal to 1/2 CD, which is equal to 12. Okay, so if we know ED is 12, then we can use Pythagorean theorem to find out OE. So it's going to be OE squared plus ED squared is equal to OD squared. And then we'll go ahead and plug in what we have to work with. So we have ED is 12. So we're going to say OE squared plus 12 squared is equal to 15 squared. This is 144. 15, I believe, is 225. Yeah, I think I'm right. So 225. And then we're going to have an OE squared. This is a plus. So we'll subtract 144 from both sides. So we get OE squared is equal to, oh, I really do need a calculator here. Okie dokie. So let's check the 15 squared. Yeah, 225. Okay, great. And then we're going to subtract the 144 from it, and we'll get 81. That makes life easy. So we're going to say that's equal to 81. We'll square root both sides, and we'll get the length of OE is equal to 9. And we're done. Right. So these properties here allow us to solve some interesting problems with circles. And what is it to sum up? It's that the diameter, if the diameter is perpendicular to the chord, then it bisects the chord. Right? We use that here. Right? OE is perpendicular to CD, so we know that it bisects it, and so CE is congruent to ED. And also that if two chords are congruent, then they're equidistant from the center. Well, we didn't use that property, but you could use that property, right, in a future problem. So if AB and RS are both equidistant away, so that means XO is equidistant, is the same measure as OY, or the same length as OY, then we know that chord AB is congruent to RS. Right? We can use that to create an equation to solve problems. So anyhow, we're going to flip it over, and we're going to do all of these problems here on the back. I'll go over them in the next video.